Okay, so the factors that affect reaction rates. We did talk about these in energy. First one being concentration. And the example in the book is that if we try and react zinc with 2 mole of hydrochloric acid, the reaction will proceed slowly. But if we react it with 6 mole of hydrochloric acid, then it's a fast reaction. And I guess what we not only need to be able to observe this or recognize this, but we need to be able to explain adequately why. So why is it that the increase in concentration will increase the rate of reaction?
Because you've got more atoms and molecules of that substance that you like.
Yeah, so we have to relate it to collision theory. Basically, all of your answers for this will relate to collision theory. Anytime you're asked to explain why something happens, and it's to do with a reaction, then it's going to be to do with collision theory. So if we increase the concentration, then we're going to increase the rate of collisions. Which increases the rate of effective collisions. Which then leads to an increase in reaction rate. So we need to explain the whole story. Now, this answer would not be full marks if you left out the effective collisions part. So just say, you say that increasing concentration increases the rate of collisions. That's not enough. And just say you leave out the word rate. That's not enough either. That's even less. Because increasing the collisions, well, the collisions will continue to happen anyway over time. But that doesn't mean the reaction is going any faster. The thing that tells us that the reaction is happening faster is that the rate of reaction has increased. So you must talk about rates and you must talk about effective collisions. And the reason why we've got more effective collisions is because we've got a greater number of collisions occurring and a certain percentage of them are going to be effective, just through the probability. And so that is why we can justify the rates and values. And then we've got an example too there on page 20, talking about the partial pressure of oxygen leading to a more vigorous combustion with magnesium. We burn magnesium in air, and you've all done that. And you've also all seen me burn magnesium in pure oxygen. And you know that it's significantly brighter burning in pure oxygen. And that is all down to collisions. There's more of the increase in concentration of oxygen gas is facilitating an increase in the reaction. The surface area, I think this one is quite intuitive, that if we increase the surface area, smaller particles have a greater surface area. Now, don't write something like that. This will not, if this is not a recognised abbreviation. So if you're trying to be quick in your answer and say increase in surface area, you will be penalised for this. Okay? You must write the words. So if there are accepted abbreviations that then I show them to you. Don't try and take shortcuts like this with things that aren't recognised. So if we have an increase in the surface area by grinding up our particles or using a powder instead of a strip of metal, for example, then all of this reasoning still applies. We can use basically the same answer for surface area as we can for concentration, which also includes particle pressure. So those two sort of fit together there. Now, for our catalysts, we talked about this last lesson. We did explain that enzymes are catalysts, they're biological catalysts. We know that enzymes have the ending A's, or the suffix A's, like amylase, etc. They are a subset of catalysts. So some catalysts are enzymes, but not all catalysts are enzymes, because we have inorganic catalysts as well. And a common inorganic catalyst is platinum. So you might see the use of platinum, which is often as a surface. And this makes sure that the orientation of whatever it is that we're reacting, so think of it as jigsaw puzzles again. It might be that because one of the reactants sticks in a certain orientation onto the platinum, it's then much more readily reactive with another reactant. And it could even be that this one's this shape, so that it doesn't really matter how the orientation for that one. It's going to be able to react with this one really easily. So this is how platinum frequently is used. We don't need to worry about what catalysts are, as in the composition of the catalyst, and we don't have to worry about how they work either. The answer for a catalyst question is going to be the same all the time for you, and that is that catalyst provides ultimate pathway lower activation energy. So E subscript A is a recognised and a totally acceptable abbreviation for activation energy. So that's what a catalyst does. The reaction remains the same as it did before. So often you're asked to represent the reaction with or without a catalyst, or what would it look like if we used a catalyst. So I would label this no catalyst. And most times there's no numbers required. However, we still need to label our axes. Now, if you're asked to do this sort of diagram for a specific reaction, you can't just write reactants and products. You have to write what the reactants are and what the products are. Okay? But this is just a generic format for this kind of thing. I strongly recommend you use a ruler. Those of you who are ruler learners, original ruler users. Whereas this one is with the catalyst. So the reaction, we're still taking the same reactants and we're still forming the same products, but this reaction occurs more readily because we've lowered the activation energy. If we lower the activation energy, what that means is that more particles will have enough energy to react. So if we think about back over here, I said a certain percentage of all of the collisions will be effective. Well, if we lower the activation energy, what we're doing is we're making a greater percentage of collisions effective. So they don't need as much energy to be successful in reacting. Does that make sense? Okay. So that's what we need to say, is that they provide an alternate pathway with a lower activation energy. And we've talked about here, this is a potential energy diagram. Because what we've got here is energy. It's reasonably important for you to get this straight in your mind that this is an energy diagram. What we're looking at is the change in energy before and after the reaction. The reason why it's important to get this clear is that there is another type of diagram that you need to be able to draw. So you need to carefully read the question to see which diagram the question is after. But let's just focus for the moment. This is our energy diagram. If I do our alternate diagram down here, and this is our alternate diagram has numbers of particles. And this time we've got our energy on the x-axis. So what we want to say is, well, how many particles have a certain amount of energy? Down here at the origin, that's 0. That's no energy. Well, this is equivalent really of absolute 0, isn't it? If we say that, if we said that, if we started our graph here, that must be wrong, mustn't it? Because what we're saying is that we have some particles that have no energy. Well, we're not. We can't have that. So that is wrong. We must start at the origin for our curve. But we're not going to have many that have low energy. We must start here, and we're going to have more and more particles that have some energy. And then it's going to tail off, where we've got less and less particles with high energy. Now, remember how we said that what the catalyst does is it changes the number of particles that have sufficient energy to react. So if I mark my no catalyst, then I'm going to say that some of my particles have enough energy to react. But if I do use the catalyst, I have not changed the distribution of the particles as far as their energy is concerned, because I haven't changed the temperature. Temperature changes how much energy particles have. And so all I've done is I've changed the finish line, if you like. I've made it easier to reach the finish line by providing this alternate pathway that requires less energy. Okay, does that make sense? So now with a catalyst, we've got many more particles with sufficient energy to react. Right, now let's look at temperature in the same way. So remember, our concentration and our surface area, we can treat them in the same way. The same reasoning applies. We must use this reasoning for the catalyst, and we can go on to then say then that our collisions, more collisions will be effective because less energy is required, etc. We can continue on with that explanation. Temperature is different again, and what we need to say for an increase in temperature increases force and frequency. And so if we're increasing the force and the frequency of collisions, same deal, we're going to increase the rate of collisions, which will increase the rate of effective collisions. But you won't get full marks for discussing a change in temperature or the effective temperature or the reaction rate if you don't mention force and frequency of the collisions. Okay, so like I said, increase And so our energy diagram is the same for the higher temperature. So it doesn't change from what we were looking at before, but it has a different energy distribution curve. And so if we look at what happens with temperature, again, here we must start at zero. We can't have any particles with energy at zero. And what we would do is we represent it, so this one might be T1, which is a lower temperature. And here is where our curve differs from the catalyst. The most common errors are getting these mixed up and drawing a catalyst curve for a change in temperature, vice versa. Because if we think about what this means, we're saying, well, how many particles have this much energy? If I add energy, if I increase the temperature, then this has to shift to the right. More particles will have more energy. The shape tends to be a bit lower at the peak, and what we're trying to aim for is a shift of about that much volume under the curve to being positioned over here. Does that make sense? That if I make it the same height, it's very hard for me to do that. That's why it's easier to get the equivalent volume between this section of the curve to be over here is by making a second peak lower. And so T2 is the higher temperature. And now, the reason why this is going to increase my my rate of effective collisions is if this here is the activation energy, only one activation energy, because the reaction hasn't changed. All I've done is hinted up the reaction a little bit, so there's only one activation energy. And you can see the area under the curve for the lower temperature has less reactive particles than the area under the curve if I hinted up. That is why increasing temperature will, I just put in there to try and highlight the area under the curve is representing all of the particles. And so heating it up, we're not changing the number of particles, we're just going to change the distribution. So we want to have the same area under the two curves. Generally, you are asked to represent this like the two curves on the same axis. So if you're asked to show what will change, don't draw two separate, like a before and an after, on two separate axes. Draw them to compare them on the same axis. And lastly, we'll talk about the nature of the reactions just very, very briefly at page 26. And this is where we're saying that reactions that can occur in solution, for example, are going to occur very rapidly. So a neutralization reaction, a reaction with an acid and a base, or a redox reaction could also be quite fast. We're talking about reactions of ions in solution, but anything that requires physical ionic bonds or metallic bonds to break tends to require more energy and won't occur at room temperature, unless we were talking about our group 1 metals, which obviously do occur at room temperature. Yeah, so it's not a hard and fast rule. It's just that we know there are some fast reactions and there are some slow reactions. One of the factors is how hard are those bonds to break. For example, if we have hydrogen gas present mixed with oxygen gas, unless we provide a spark, they're not going to ignite. It needs a bit of activation energy, thankfully, otherwise there'll be random things exploding all over the place. Right, so this is all the theory for this booklet. If you look, you'll notice that the rest of it is just a few pages of questions. It starts at question 21 and it goes through to question 45. So you can spend the rest of your lesson finishing off these questions.